Hello and welcome back to Calculus 3, section 14.3 on conservative vector fields. So before we do conservative vector fields and calculations for potential function and else, we have to go through few definitions. So I'm going to split over here this area into 4 parts, and I'm going to draw these curves that we want to consider. So all of these are those parametricized curves that we have. So now we are going to give them names. You see that the one on the top left is closed, right? It's connected, right? And that's something that we'll call closed and simple. The one on the bottom is closed, but it's not simple because it intersects itself, right? So not simple.
Does it matter if it intersects itself once or twice?
Or 17 times.
Okay.
Yep. Now, the one on the top is obviously not closed. It's not closed. And then but it's simple because it's not intersecting itself. And the one on the bottom is not closed and not simple because it intersects itself at least once. So these are the words that you are learning now and pertains to a certain situation. So that's one of them. Now we're going to split the space again into 4 regions and talk about regions the same way. So now I'm going to have the potato one. So this is a region, so the whole thing over here, right? We call this region R. And this is going to be connected and simply connected. Actually, let me draw all of them first, and then we'll talk about them. So,
This is a new thing.
Good thing you're paying attention.
Stop. These ones are filled in. I still don't totally understand how something can be like not connected but still simply connected. I don't understand. What?
As my high school professor would say, you're not supposed to understand until you learn. All right, now we'll take a look at it.
Like I get what it's referring to, so.
Well, those are definitions. You are learning words. I mean, that's what it is. Okay, so let's put. So this is connected. Not simply connected. And then not connected but simply connected. And not connected not simply connected. So this business of simply connected is clearly related to whether it has a hole or not. And simply connected means, can you draw a straight line? Not straight line, any line. And every line that starts in a shape has to be in a shape without crossing the opening. So you see, if I have something that is connected, right, I can get from any point to any point. This classroom is connected, so we can get to any point. Two islands are not connected unless there is a bridge, but there's two islands are not connected, right? And then you also see that the same connected, connected, and not connected, not connected goes to the other two, right? Now, simply connected means each point goes to each point, right? But there are no holes that you have to go around. That's a simply connected. Over here, not simply connected because I can't go in a straight line this way because I would leave the region, right? Because there is this part in there. So not connected, not simply connected is just those two worlds combined, obviously. So now our definitions in the future will say, let region R be simply connected, right, and so on, and go on. And then you know what it means because you studied these graphics. Now we are ready for the definition of the conservative vector field. So, a vector field F is said to be conservative on the region in R2 or R3 if there exists a scalar function phi such that del phi is equal F on that region. So I told you that the function can produce the vector field if you use it right in a gradient. So here is the definition for conservative vector field. So you know that if the vector field is conservative, that there is a function that generates that field. So that's just the definition, right? We are going to work on problems, and then when you are working in the field, right? You will measure the field, and then you will test whether the field you measured, right? You model the field, and then you will check if the field is conservative, and if the field is conservative, you will be able to find the potential function which generates that field. And once you have a potential function, you understand the concept that you are observing. So whether that be ocean currents or wind or whatever you're trying to learn. So what is the test for conservative vector fields? Now this is important. Do what? That's what I thought. Test for conservative vector fields. So the test is these three equalities of partial derivatives, and if they all hold, you have your conservative vector field. If one of them fails, or more than one fail, then the vector field is not conservative. It's still a vector field, it's just not a conservative vector field. Now, what that means is you might not be able to find the function which generates it, right? All right, so we have delta f, delta y, right? So df, dy is dg, dx. Partial, yeah. Partial f, partial y is equal to partial g, partial f. So then we have partial f, partial z needs to be partial h, partial x. And finally, partial g, partial z needs to be the same as partial x, h, partial y. So these are the three that you have to run to check if the vector field is conservative, right? So this is obviously 3D. If you have this one over here is only for 2D, right? And all three are for 3D. Maybe I should just put, let me put, it's better if I put r squared and r cubed. Don't feed the trolls, right? That's the one, don't feed the trolls? All right, so let's test conservation. So say your vector field is given by 2xy minus z squared, comma x squared plus 2z, comma 2y minus 2xz. All right, so let's test. So I have to test partial f, partial y needs to be the same as partial g, partial x. Is it? Well, partial f, oh, by the way, if you are struggling, this is f, this is g, this is h, right? So partial f, partial y is 2x. And then that needs to be equal to partial g, partial x is 2x. Okay, it passes this one. Move to the next one. Is partial f, partial z. Needs to be the same as partial h, partial x. So partial f, partial z is negative 2z. And that needs to be partial h, partial x, negative 2z. Passes. One left. Partial g, partial z needs to be the same as partial h, partial y. So partial g, partial z is 2. And partial h, partial y is 2. Nice. It passes all three. So, yes, f is conservative vector field. And that's always exciting, as you can see. Yeah.
It's like you didn't even mess up.
When do I?
Professor? So like, exactly what conservative means.
Conservative vector field means that the vector field has the scalar function which created it. So we are going to find that scalar function now. So it will be clearer in about 10 minutes, 15. Push 20. 20. It's physically impossible to get ahead of yourself because yourself occupies a space that is finite, and you can't.
You're saying I can't run into.
What about quantum theory, where I can meet just at once?
That's a theory. You just said theory.
Just let's leave it there. So let's also take a look at the field x cubed minus xy comma x squared over 2 plus y. So this is clearly in R2, right? And it's since it's R2, we only have that one condition that we need to check. If it works, that it's conservative field, let's find potential function. Who's excited?
Yeah.
There we go. That's +5 on the final now. Nice.
More enthusiastic.
So partial f, partial y needs to be same as partial g, partial x. All right, so partial f, partial y is negative x. And partial g, partial x is x. And not conservative. Failed.
No.
Yes.
Not conservative.
Yes,
It's liberal.
It's liberal. It's liberal vector field. Very good.
If I write, if I write it's liberal,
No. Do what?
There weren't department regulations.
Oh, you had no idea how awesome my classes would be.
What's the extra watch for outside?
Yeah.
It's just both of them are divided by it.
I mean, you could just distribute that to be inside the vector, right?
Yes, that's exactly what I'm going to do now. So this vector is written as x over x squared plus y squared, comma y over x squared plus y squared. And we are going to test. See, in differential equations, you say we're going to test for exactness. Over here, you're using different wording. We are testing the conservative vector field. So we have partial f, partial y needs to be the same as partial g, partial x. All right, so what is the partial f in respect to y over here? What's the derivative? Yes, okay. So it's just negative and that's it.
Negative 2 over 1.
Negative 2 over 1.
Negative 2 times 1 over 1. And then that. I'm going to do the 1. Yeah.
Don't you love it when when you are struggling with the chapter 12 concept in chapter 14? No, I mean it's interesting, right? Not.
It's interesting. Really?
All right, so
I don't want to do the quotient rule. I'm too lazy.
you don't want to do quotient rule, then don't.
I don't want to.
Exactly, it's not a quotient rule question.
So just don't go to college.
So, guys, the first order of business is to see that these two equations are symmetric. Yeah. If x equals y, you swap x with y, that means that the partial derivatives are the same. So it is conservative just by making that observation. You're done. But then we still might want to be able to do chapter 12 derivative to show that. So let's. So how about we take the partial derivative in respect to y of x over x squared plus y squared. Well, first of all, the x is not y, so we can kick that outside as a constant and just focus at the derivative of 1 over x squared plus y squared. Now I can rewrite. Okay, I'm treating this as a calculus 1 thing. You've never seen the derivatives, so I'm writing out everything. Now we have partial y, and what I'm going to do now is I'm going to write this as x squared plus y squared to the negative 1. Now x equals, and when I'm taking the derivative, it's going to be negative 1, and then we copy the guts to the negative 2, and then we take the derivative of the top, which is derivative of the inside, which is 2y. So what is the final answer over here? Is going to be negative 2xy divided by x squared plus y squared, everything squared. You're asking this x? This x is this x. Because we're differentiating in terms of y, it's a constant, you can kick it out. So now we found that the partial f partial y is given as negative 2xy divided by x squared plus y squared, everything squared, which actually will be the same as partial g partial x, which you can go home and practice, right? Because you care, right? Right. Now, once we show that this is conservative vector field, it is time to find the potential function.
Yay!
There we go. So let's write some of the truths that we know so far. If I am to have this potential function phi, which is a function of x and a y, and I take the del of that function, I will get the vector that is phi x of xy and phi y of xy. Yes, we're going to find the potential function now. So this is what I have, guys. I have this. Now, please observe that this part over here is the f part, and this part over here is the g part for our vector field, which is where you are going to make the claim that phi x, by the partial derivative of phi in respect to x, is equal to f, which is given in terms of x and y, right? Maybe I should also note that here. For emergencies, they have to land here, so...
It is legitimately right there.
Yes, it's going to land right there. So...
Is there an emergency?
Well, yeah, if they're landing there, yes.
Oh, there's fire trucks over there.
Oh, yeah. Like in that big ass truck.
Yes, that as you're entering the college, there is the field on the right is where they're
I don't think we're going anywhere anytime soon.
Yeah, I guess someone's
No, there's an
gonna
exit.
Yeah, there's a sign exit.
Yeah.
And if you go out by the lake,
Thanks for getting in everyone's way. Let's go.
Yeah, that's gonna cost them about 10 grand.
What do you think? If they're getting medevacs, there's
Probably
someone
car
really
accident.
died.
Yeah.
Someone's really in trouble.
Someone's probably taking those turns too hard.
Or
Jeez. It's the goddamn.
Well, I mean, like, if they're getting medevacs and they cross them into a hospital,
Yeah, we have to wait for the helicopter to finish, and then we'll
This is
continue.
going to be the most exciting lecture for you Scandinavian viewers.
Go outside.
let's not dock and someone who's been docking.
I can't pause the stream because it just creates a new file then. So
Just tell everyone to take a 5-minute break on the stream.
no, they're gone. All right, so let's go.
I still see the no, it just landed. It's going to start up again, and then we're all going to have to come back over here again.
Don't say have to come back over here as if watching the helicopter is a necessity. We will survive without watching it. I guarantee you.
Yeah, we can just close the windows.
I know. I'm still here.
All right.
If you want me to not look, I won't look.
So guys, partial derivative of phi in respect to x. I was stalling, waiting for it to come back. So you're welcome.
The helicopter.
Is equal to the f, which was x over x squared plus y squared. Now, if you learned anything in your short exposure to differential equations in Calc 2, you know that separation of variables, right, helps in this case. So if I write this as partial phi over partial x is equal to x over x squared plus y squared, well, then this dx move to the other side. I'll have partial phi is equal to x over x squared plus y squared, and then dx. And now I can hit both sides with the integral. Boom.
Boom.
Now, what you have on the left-hand side, integral of d phi is just phi of xy. Isn't that what you are looking for? We are looking for potential function phi. And on the right-hand side, well, I have to integrate, right? And hopefully for that, you will be using u sub, because this is basic u sub problem. So for the u sub, I have that u is equal to x squared plus y squared. Du is derivative. Now, since we are dealing with respect to x, this is just 2x dx, and the y dies because it's a constant, right? Now, I don't have 2x, so I have to fix it. So here is a 2.5 in front. And the whole integral now becomes 1/2 integral of du over u, which is 1/2 ln absolute u plus, and here is the $1 million c of y.
Why the what?
Because we reversed the partial derivative in respect to x, which means that when you are taking partial derivative of x, if there are any terms that are only in respect to y, that are only function of y, those terms would die. So the c is no longer plus constant c, is now plus function c that could be a constant or could be a function of y. So when we add the constant now, it's going to be this. So now, what is the phi of xy? Phi of xy is 1/2 ln absolute value of, I don't need absolute value because both of these terms are squared, so they're positive. So I have x squared plus y squared plus some c of y. Now, I'm going to actually box this slightly because this is technically an answer. If you are to take the partial derivatives of this, the del, right? If you find the gradient for this, you will get the vector field that we are looking for. But we have this issue now that we actually have c of y, and we want to know what that is. All right. Now we can calculate that. So what is the only thing we actually did? This is all one step here. If you look, all we did is we said that the partial derivative of phi from the gradient is equal to f from our field, and that's always given to you, right? And then when you write phi x is equal to whatever the function is, when you do separation of variables and integrate, you get your phi. So this is a standard thing that you did in your Calculus 2 when you did the basic separation of variables for differential equations. Now, look what we can do. We can now take the partial derivative of this in respect to y. And when you do that, you can equal it to g.
What?
Yes, equal it to g. And you will be able to find cy from there. So now we have, when I take the partial derivative of this, right, we know that we copy 1/2. Then I put this as a denominator, and then take the derivative of this in the numerator. There we go. Plus c prime of y. Because we took the derivative of function that it's y in respect to y. So it's enough to write c prime. It's fine. Now these twos cancel, and what you have now is that the phi y is y over x squared plus y squared plus c prime of y. Now, compare this to g xy, because phi y must be equal to g. So now what I have is that y of x squared plus y squared plus c prime of y is equal to g, which was y x squared plus y squared, from where we get that c prime of y is equal to 0. When you integrate both, well, you can differentiate this now, so you will get dc is equal to 0 times dy, and you integrate both sides, you will get c, which is the function of y, is equal to 0 plus some constant, let's call it constant k. So now replace in phi xy, the one that we boxed. So what we boxed is that phi xy is equal to so phi xy was equal to 1/2 ln of x squared plus y squared, and then we had plus c as a function of y. Now we have plus 0 plus k, so it's just plus k. And this is it. So this is the potential function which will generate the field we had. It's time for us to do this in R3. Yeah, this is the quick problem. Problem 22. Vector field is given as yz, xz, xy. What is the potential function phi of xyz, which would generate this field? Well, if the field is conservative, right? If the field is conservative, and if you do the all of the calculations, in this case there will be 3 stages. It's obvious that the function that creates this is x plus y plus z plus k. I mean, x, y, z plus k, and you're done, right? It's obvious.
Oh yeah, done.
Simple. Now, yeah. So the answer is that, and just move on. But let's do some calculations to fill in some lines. Might be, right?
You know, we should just get it done.
Oh yeah, I forgot. Today was quiz 7, right? That's why I showed up.
Yeah, I totally.
This kid's not a ninja anymore. We got caught.
We got caught. All right.
Does everyone in the class then?
The what?
Does that mean everyone in the class?
No, there was some kids who just smart about that.
Yeah, some people left already.
Some people are actually good at
Yes. All right. So what do we have?
this.
We have that the del phi is going to be phi x, phi y, phi z.
What is going down?
Nah, I'm just gonna put more stop signs. So what we have is this situation. Now we see the one-to-one correspondence between these. We are looking for phi. So we are going. You can start anywhere you want. You can start anywhere you want. I'm going to start with phi x is equal to yz. So phi x equals to yz. So that means that the partial derivative of phi divided by partial derivative of x is equal to yz. Separation of variables says that the partial phi is equal to yz partial x. And then we... What happened?
Someone better die.
She said someone better be dying.
Wow.
We had the
Wow.
There's an ambulance, another fire truck, and a police car now.
See.
Like extra.
And then...
This person's just like, I don't care about insurance. I just want...
And then someone is going to tell me that guys are worse than girls. No.
Yeah, I think she just.
It sort of seems like you're making a generalization off of one horrible person. But like, okay.
All right. Well, I hope that the others are going to jump in then.
I just want to see a helicopter.
All right, guys. So stop with the helicopter. We got to get through the 3D problem. Yes.
I didn't see the helicopter. Our
Guys, shh.
How f and phi are related.
What happened?
Can you just repeat how f and phi are related?
Like this.
Please.
Okay. So let me let me give you an example. Okay. Let's say, so this is unrelated to this problem, and I will erase it also. Pay attention, and you have one shot in getting this now. Say that the potential function of xy 2D is equal to 3x squared y minus y squared. So this is a scalar function that we learned in the first day or chapter 12, right? So that's it. Now we used f over here. Now we are using phi. Now, if I find del of phi, that means take the partial derivative in respect to x of this. So that's going to be 6xy. And then, comma, take the partial derivative with respect to y. That's going to be 3x squared minus 2y. All right? Now, see, this thing over here has the same form as any f of xy we learned. So now, if f is given to me, so technically what's given to me is this, which is this. And now I can, so if f, the vector field is given to me, that's this. And now I know that the first component is the phi of x, and the next one is phi y, and then phi z. So that's what I have so far. All right, so that's that part that I just explained the relationship, and that's in the definition, right? The first definition I wrote for a conservative vector field. It says vector field is conservative if there exists phi so that its partial derivatives are right, the gradient is like the del. All right, good. So now, when I equal the first one to phi x, because f is equal to phi x, right? And then I separate variables, and I eventually integrate. I get the answer. This is the answer to the problem. fxyz is phi xyz is equal to, and when I integrate in respect to x, like yz is a constant, right? I'm integrating in respect to x. You see the dx at the end. So it's just going to be xyz, yeah. Plus some function c in terms of y and z. Because if I take the partial derivative in respect to x, right, whatever is in here would die, because there are no x's, right? So when I am undoing this as the antiderivative, I have to leave possibility for this to be any function in terms of y and z. So now I'm going to box this lightly, right? Because this is not the final answer to the problem, but it's a pretty good one, right? It's the best we have so far. All right, so what I'm going to do next, I'm going to take this problem now and take the partial derivative in respect to y. So I'm going to find phi y, and phi y is going to be xz plus partial derivative of c in respect to y. Right, that's what I'm getting.
Why are you choosing y?
I could do z, it's fine.
Okay.
But let's just go in order. Let's go OCD.
Okay.
And I'm going to set this equal to whatever phi y is here, and that's xz. Okay, so that's xz, right, from up there. Now, from this equality, I have that partial c partial y is equal to 0. Left-hand side xz, right-hand side has xz, they're equal, so partial c partial y has to be 0. Do the separation of variables again. We have that the partial c, remember c is a function of y and z, right? So partial c is equal to 0 times partial y, and integrate both sides. When you integrate both sides, over here, you are going to get that the c of yz is equal to 0 plus, and you are getting just c of z. Now, we integrated in respect to y, so the answer, what's the integral of 0? Integral of 0 is 0, right?
Yeah.
Plus constant. But constant is going to be in respect to z now. And now, plug in. So you plug in. The new and improved solution is phi xyz is equal to xyz plus, and instead of c of y and z, I just have c of z now. It's much more fun in differential equations in here, but it's okay. All right, so now the final step is to differentiate this in respect to z, because we want to figure out what this is. Yeah, it's going to turn out to be constant, but that's okay. So phi z is equal to now xy plus c prime of z, and we set that equal to our xy, which is the phi z from the setup of the problem. That was age in that. From this equation, we get that c prime of z is equal to 0. C prime is dc dz equal to 0. When we separate variables, we get dc equals 0 dz. and then we integrate both sides, and we get that c, which was supposed to be a function of z, is equal to 0 plus some constant k. Plug in. So finally, as I promised, your potential function s comma y comma z is equal to xyz plus k. And that is the end of the problem. Next time when someone tells you, what do you know? Work this one on 16 napkins when you're outside, and they will see the power of...
It's going the other way. No.
Yeah, we are not done.
Oh, you did look.
I'm down to change his route to the hospital just so you can get a glimpse of them.
Yeah.
Come back, I'm more important than the time.
Sorry.
If they were dead, you probably wouldn't call it a helicopter.
Sometimes they do actually.
Oh yeah.
If they're organ donors, sometimes they will to save the organs.
Anyway.
The officer like taking out the car. It's like, here's an organ donor.
Yeah, the helicopter is still lingering, so yeah.
Well, they still have, even if someone like looks dead on scene, a lot of the time they'll have EPN anyway because they can't really, only certain people are allowed to call dead. I mean, even EMTs aren't allowed to sometimes. In some jurisdictions, understand that they call it, or in like certain situations.
Is that a slipping hazard?
Yes, and the helicopter already left. Anyway, so the next question, and I don't know if you are begging for this question, why would we look for a potential function? What could we possibly do with the potential function? Well, you know what?
Make a kinetic function?
There is no. There is a fundamental theorem for line integrals. Yes.
Oh, yeah.
Now, if you are going to recall fundamental theorem of calculus part 2 from your Calc 1 class, you would probably, part 1, you would just recall the thing that you use to calculate definite integrals, where integral a to b of f of x dx was computed with any antiderivative a to b is equal to, right, f of b minus f of a. What is the fundamental theorem for line integrals? Guys, it's going to be phi of b minus phi of a. The potential function that we find over here is the antiderivative that we need to compute the line integral, and that saves a lot of time. Now, if you have the potential function, it saves a lot of time. If you have to spend 25 minutes figuring out potential function, you might as well crank the integral in the first place, right? So, nice. So now we have to write that down. The line integral on the closed curve is going to be 0, right? Line integral on the closed curve is going to be 0. I'm trying to find where is the... There it is. Fundamental theorem for line integrals. FTC for line integrals.
What does FTC stand for?
Fundamental theorem of calculus, yes.
So this works only when it's conservative.
Yes.
So
So,
if it's not conservative, I just 14.2.
yes. Yes. So both sections 14.3 and tomorrow's 14.4 are actually sections that are quality of life sections, where if you have these certain conditions, if certain conditions are met, you can use the shortcuts from those sections. So fundamental theorem calculus, if you have the potential function, right, because your field was conservative, you don't have to compute line integrals. You get to subtract two numbers, and you're done. Rather than having the, the lengthy calculation with all those dot products and things that you have to worry about in your previous section. So it's much easier to subtract two numbers than do all of the other things. And tomorrow is going to be pretty much the same thing. If certain conditions are met, instead of calculating the line integral, you will just be setting up a double integral over area and computing technically 13.1 or 13.2. So it goes back and loops back to. So both of these sections are technically shortcuts on what to do if you have certain types of vector fields show up. So now, what is our fundamental theorem of calculus for line integrals? So the good old line integral from 14.2 for the vector field that was given as f dot t ds can be computed as the line integral. So f dr, we know that from the yesterday's lecture, and that's just going to be simply fb minus, phi of b minus phi of a, which is the subtraction that you get at the end. Now we're going to take a look, obviously, at the example of this, so it makes sense. Now for all points a and b and piecewise smooth curves oriented from a to b. So these a and b are points, guys. I have to tell you that point A, so you're not completely lost, your point A is going to have coordinates x1 and y1. That's a point somewhere in space. And point B is going to have x2, y2, and that's another point. Because remember, this function phi is in terms of x and y as a function, and or xyz in this case, that previous case, right? So in your case, in that case, A would be x1, y1, z1, and B would be x2, y2, z2, and you will be computing them in here. It's phi of B, so you will be plugging in these coordinates. So your point B might be 2, 3, right? And that goes into the phi equation. Yes.
So are you for a test question, are you going to ask us to come up with that phi equations and then plug in points, or is it going to just be like
phi? So if the phi equation is given, right, and you have the vector field. So guys, focus. Look. So let's say that your phi of xy worked out to be 1/2 x squared minus y squared, and you had the vector field of x negative y. So there you go, and you are looking for the integral, the line integral, where c is given to be the quarter circle from 1, 0 to 0, 1. So yeah, so quarter circle from A 1, 0 to B 0, 1, right? So if you are going to do 14.2 on this question, well, you will just do the f dot r prime, but r, since this is a unit disk, and you need to know that it's parametricized cosine first and then sine, because it goes 1, 0 to 0, 1. And then you would have to use your t, which is 0 to pi over 2, because it's only quarter circle. And then you will dot the vector field, which would be cosine t, comma, negative sine t, with the r, that you r prime when you have to, right? So it's a process, right? It takes time to figure out what this thing is if you are using line integral for the vector field. If you have the potential function, the answer to the question, what is the line integral of f dr, is simply phi computed at 0, 1 minus phi computed at 1, 0. And that calculation should take less than 18 seconds, because we have 1/2 in a parenthesis. I have 1 squared, so I have a 0 minus 1 minus 1/2, and in parenthesis over here I have 1, right? So this is going to be negative 1/2 minus 1/2. It's negative 1, and you're done. No. But see, the trick is that what I would like you to do is I would like you to, now when you get home, first thing you do, right, before eating or showering or whatever, is to actually crank yesterday's problem on this and make sure you get that. Now, clearly it's going to be half a page to a page calculation, because you have to use all of the...
Simply just
This. Do the line integral for vector field. Do the line integral for vector field.
See, I got some lab projects to do, so I'm quite
You really want to know the hack.
Okay.
I think that's a hint that this is on the phone. What?
So that's it, guys. Tomorrow, Green's theorem. So yeah, be ready.
Wear green tomorrow, everyone.
what? I don't know. You know, I think